Hi, so today I'm going to be talking about the soft margin case of support vector machines. If you're watching this video, I'm going to assume that you're already familiar with the hard margin case and generally what support vector machines are. I will recap a little bit, but only go through things briefly, but just because it's so important to segue into the new material that we're going to cover. So, support vector machines are used to solve classification problems. So here's a simple example. You have a data set with two independent variables, two x variables, and a binary y variable. We call them classes -1 and +1. So we know x1 and x2 for a whole bunch of training data, things that we already have the y values for. And then we have a new observation where we know the x values. We want to try to classify the unknown y variable as either belonging to the -1 or the +1 group. So here for this simple example, we have these known -1 points, these known +1 points. We want to know if we get a point here, should we think it would be -1 or +1? These could be anything depending on our application, what the meaning of the classes are and the x variables. So a support vector machine does this classification using a hyperplane in the space of the independent variables, the x variables. In a 2D case, a hyperplane is just a line, so that makes it simple to plot for us here. But there could be more x variables. So in 3 dimensions, a hyperplane is just a plane, and so on and so forth for higher dimensions. The support vector machine, this is the hard margin case, uses the maximal margin classifier. So it just picks the hyperplane with the largest margin between the observed data points. So this would be a worse classifier. It's closer to some of the training data. So if you get a new point right here, it's above the hyperplane. You would predict that that point would be a +1, when in fact it's quite close to the -1 points. For this case, which is the better classifier with the bigger margin, a point over here at say 1, 3 would be classed with the -1, which seems more accurate. So that's where maximizing the margins gives better classification. So a support vector machine will consist of one hyperplane, that's the classifier, and then like we saw in that last slide, 2 other hyperplanes that are parallel to that for the lower and upper margin. These are the equations with vector W being a vector of weights, one for each x variable, basically like coefficients of the x variables, minus b. So when that equals 0, it's the classifier. -1 and +1 give the lower and upper margins. And so to determine the classifier, we only just need values of w and b. That'll give us the equation of these lines or hyperplanes. So here's an example just for the 2D case. We have these 3 lines are all we need for the SVM. So determining the location of the hyperplane is an optimization problem. So the decision variables are the values of w and b, basically just the equation of the hyperplane. So we're deciding where that hyperplane is going to go. The objective is to maximize the distance from the hyperplane to any of the training data points. That's maximizing the margin that we were just talking about. And so that distance is 2 divided by the length of vector w. And in 2 dimensions, the length of vector w is just square root of the sum of the square of each component. That's basically just like the Euclidean distance of that vector. So the objective function here is to maximize 2 divided by length of w, and which is equivalent to just minimizing the length of w. And so there is one constraint for each data point. Basically, that's because each data point needs to be on the correct side of the margin for its class. So that gives rise to one constraint for each point. So letting y be the variable for class and n be the number of data points, these are each of the n constraints that we would get. So in that simple example we saw, we would just plug these points into this equation. And so, for example, for 2, 1, we would get minus 2w because y here is negative 1, minus 1w, or just minus 1w2, plus b, again, because y here is negative, we end up with a positive b, is greater than or equal to 1, and so on and so forth. So then solving this example with 4 points, we did this in Excel in the last, or actually I think it was 2 lectures ago. We ended up with the equation of the separating hyperplane. W1 is 2/3, W2 also 2/3, and B was equal to 3. That's this L1 in the graph here. And we noted that only some of these points have an effect on the location of the hyperplane. And these are called the support vectors. So here we had 3 support vectors that lay directly on these margin lines, L2 and L3. These are points 2,1, 0.12, and 0.33. 0.44 in the optimization problem had slack. That's this point here, meaning that it had room to move around without affecting the solution to the optimization problem. So far we've only seen linearly separable data where we could actually draw a line that goes directly between all the data points with none on the wrong side. So that example we saw before had a hard margin. We didn't allow any points to be on the wrong side. Sometimes we have data where that's not the case, and quite often that happens, in fact. So if we want to use a linear support vector machine for that kind of data, like we see on the right side here, we would have to use what we call soft margins, which allow some points on the wrong sides. You could imagine also, well, so first of all, you can't draw any line through this that would put all of the red points on one side and all of the blue points on the other side, like you can here. You could imagine if we were allowed to do something other than a line, you could do something maybe like a parabola going with the red points above the parabola, the blue points below, but we can't do that because we're only considering the linear case right now. And we're not going to, in this particular talk, go over nonlinear support vector machines, but those do exist. So now that we're softening the margins, we are allowed to choose a hyperplane with points on the wrong side of the margin, or even on the wrong side of the hyperplane, so misclassified entirely. So then what is stopping us from picking really weird or bad classifiers like this one, where every blue point is on the wrong side, the margins seem to be just kind of at random. So we need to figure out some way of introducing constraints on this so that that doesn't happen. So we want to penalize the poorly classified training data, like in this case. And then we want to consider the total penalty when we're picking which type of classifier to use. So for the hard margin case, we thought of the margin as sort of an off-limits sign. It meant that cannot happen, there's just no way. Now, with soft margins, the margin is sort of a warning, and as you have more and more points misclassified further and further away, the alarm bells start going off more and more saying don't use this particular classifier. So in this case, we see if the red group is considered to be more towards 0, 0, and the blue group is towards higher values of both x1 and x2. Here we have 1, 2, 3, 4 points on the wrong side of the classifier entirely. These two red points also on the wrong side of the margin. These two blue points on the wrong side of the margin. That's all very bad. So here we just have 4 points slightly off. That's a little bit better. So another point in how we want to set up the soft margin case, larger margins are still better as they were in the hard margin case, since we do still want to have more buffer around the training data to get a better classifier. But now we can technically just make margins as big as we want to, like in this case on the left here, with just absurdly large margins. So what's to stop us from just getting bigger and bigger margins? So we need to have a trade-off between making the margin larger and then ending up having just every point on the wrong side, because that's just there's just no point to that. So we're going to introduce a cost for each misclassified point. So each point I has an associated variable xi sub I. That's going to be basically the cost for that point. So if point I is directly on or on the correct side of the margin, there's no cost. That will just always be 0. So no matter how far on the correct side is, that's just no cost. But if it is on the wrong side of the margin, then that value is going to be greater than 0, and it's just going to go up from there, depending on how far it is. And then the objective function is going to include a term for the total cost of all of these misplaced points. And that term is C times the sum of all of the xi for I from 1 to n being the total number of points. C, which we just introduced, is a tuning parameter that we can just select of our own choosing, depending on how much we want these errors to affect the classifier. So as this goes up, it multiplies all of the errors more, meaning the errors are considered to a greater extent. So continuing with sort of the meaning and how the x's work. So for each point that has a vector x of x variables and a y variable, xi is going to be defined as the maximum of either 0 or 1 minus y times vector w dot product with that point's x vector minus b. And why do we choose this particular value? Why do we want xi to be that? So it's defined this way so that they will take on predictable values based on what side of the hyperplane or margin each point is on. So remember we saw earlier, and then I recapped at the beginning of this presentation, this is the equation of the hyperplane. And this is actually 2 equations of each margin for the 2 different values of y. And this looks familiar. The definition of xi is familiar from these equations of the hyperplane and the margins. So we can think of 3 different cases depending on the value of this term, the yi w dot x minus b. So case 1, that value is greater than or equal to 1, which, as we saw from the last slide, that meant that we are on the correct side of the margin. Because if yi is -1, then this term is greater than or equal to -1, which is the lower margin. If that's +1, this term is greater than or equal to 1, which means that we're on the correct side of the positive, the upper margin. Case 2, when this term is between 0 and 1, that means that the point is going to be between the margin and the hyperplane. Case 3, if this is 0, then it's on the incorrect side of the hyperplane entirely. So we'll go through very briefly. This should follow pretty naturally. But for the first case, like we talked about, these were essentially just the constraints from the hard margin case. And so when that's the case, when this term is greater than 1, 1 minus something bigger than 1 is going to be negative. The maximum of 0 and a negative number is just going to be 0. So the whole thing, C, is just going to be 0. Case 2, when this value is between 0 and 1, meaning 0 being on the correct side of the hyperplane, but less than 1, meaning incorrect side of the margin, then this whole term, 1 minus something that's between 0 and 1, is also going to be between 0 and 1. So C will just be between 0 and 1. And then the last case, if this value is less than 0, then 1 minus something less than 0 is going to be greater than 1 because you're adding essentially a positive number at that point. So C is just greater than 1. So now we know some information about these costs. We can interpret them a little bit. So how do we incorporate them into the programming problem so that we can then optimize and find the best classifier? So the objective function is definitely going to want to minimize the total cost like we talked about. So now how do we incorporate it further into either the decision variables or constraints or both? If we were to just look at sort of an intuitive method briefly, what if we just kept the decision variables as they were before, just W and B that give the location of the hyperplane, that give its equation, and then we just define C like we did explicitly on the previous slides, and we only need to know W and B from the current solution if we're solving this like iteratively, for example. Nothing extra to choose. There's no new decision variables introduced here. As it turns out, including this maximum, when you can actually solve this in Excel just with this function by trying to minimize the objective function that includes this. Which is kind of cool, but unfortunately I'm not sure what programming algorithm can actually handle this max function within the objective function. So we're going to look at sort of a more formal way of going about this that we can solve. So standard method is going to be introduce decision variables also for C sub I for all I, in addition to the W and B decision variables. So the constraints are going to be set up to make sure that these take on the values that we want. At first it was counterintuitive to me that we would make these be decision variables where we should really already know what they are, but this will all play out, as we'll see in a moment. So to have this be the case, that C equals this value we want it to, we need 2n constraints. So 2 constraints for each data point. So one is that C is greater than or equal to this quantity. And then the second, that C is greater than or equal to 0. And then ultimately we'll be able to use quadratic programming algorithms to solve this. So we're going to get further into all of those steps we just talked about. That was just sort of a brief overview. So we're going to get into more detail now on how the objective function is going to work. So this is the objective function, minimize z equals the length of w divided by 2 plus c times the sum of c for all I. So this first term is the same as the hard margin, but there's this new term for cost added in. The first term, like before, prefers having a larger margin. Remember, 2 divided by w is the width of the margin. So minimizing length of w maximizes the margin. Second term prefers fewer errors in where the points are located. So if you have points with higher C, which is meaning larger and larger errors, this value is going to go up higher and higher. So if you minimize that, that means you have fewer and fewer errors. So increasing the tuning parameter C, like we briefly touched on earlier, makes minimizing the sum of the errors more important than minimizing this. So it's really maximizing the margin versus minimizing errors are what these two things are doing. And C sort of determines how important one is relative to the other. So a common choice for C, we can really choose anything we want to depending on our application and how the data look. Common choice is C equals 1 divided by n. If you think about it, the sum of C from 1 to n divided by n is basically the average value of C. So that's frequently a starting point that people use. Can note also here that if C were just 0, the whole term here would equal 0, and then we would just have the objective function from the hard margin case, and we'd only be trying to maximize the margin at that point. So you can see the behavior as you reduce this further and further, you just get closer to only wanting to maximize the margin. So now we'll get further into detail of the constraints that we mentioned earlier also. Like we talked about, there's 2 constraints for each data point. The cost constraints, the y sub I times the quantity of vector w, there should be a dot product in there, with x minus b greater than or equal to 1 minus c for all I. So remember that the hard margin constraints were this quantity greater than or equal to 1, and that meant that points had to be on the correct side of the margin. The soft margin constraints basically are the same, but just with the c subtracted from the right-hand side, meaning that points can be beyond the margin and they're limited in how far they can be by the value of c, which makes sense and is sort of what we wanted to accomplish. So then there's also non-negativity constraints. So c has to be greater than or equal to 0 for all I. So the reason for this is that if c could be less than 0, then that would mean that there's a negative cost associated with points on the correct side of the margin. So correctly classified points from the training data would be subtracting from costs. But this goes against kind of one of the main features of support vector machines, which is that only the points on the margin, or now in the soft margin case, on the incorrect side, can affect the classifier. That's one of the main things about support vector machines, that we call those points the support vectors, and anything on the correct side doesn't really come into play. That has no effect on the classification rule. So here's, now that we've talked about all of that, this is just a summary to make everything crystal clear. So the hard margin case, each point must be on the correct side. Soft margin, some are allowed on the wrong side. Decision variables, in the soft margin case, we add the xi sub I for each observation. The objective function, we add this cost term. The constraints, we now allow points to be on the wrong side of the margin within the bounds given by xi. Xi here also, though, isn't a absolute distance. It's sort of more of a proportion based on the size of the margin. And then also that the xi sub I are greater than or equal to 0. And then the support vectors, before were only points lying directly on the margins. Now that points can be on either side, the support vectors either lie directly on or on the wrong side of the margins. So now how do we actually go about solving this? So we have the problem that we just set up, that we just mentioned. Looks kind of like a linear, or not linear, but a optimization problem. So the length of vector w in the objective function, first off, we can notice that that involves a square root, because remember that was the square root of the sum of the squared terms of w, the components of w. So we can minimize w squared instead, which is just sort of a quadratic term. That's w1 squared plus w2 squared plus w3 squared, and so on, however many w's you have. So that's a little bit easier to solve right off the bat. Also, for sake of computation by computer, in practice, people take the dual of this problem. It's going to reduce the number of constraints, which, as we saw earlier in this class, reducing number of constraints can greatly improve computation time and efficiency. And there is the Lagrange method for getting the dual of a nonlinear programming problem. So here is the dual. Even though this is the method used to solve this computationally on a computer, for purposes of sort of seeing it geometrically, I'm going to, when I solve it, use just the primal method. When I was first researching this topic, all of the sources that I was seeing seemed to indicate, don't bother with the primal method, just go directly from that to the dual method to solve. I think that's because most sources that I was seeing were geared towards somebody implementing this in a computer, I would imagine. But for purposes of just purely visualizing things, I actually found the primal problem to be really useful. But we'll note that what you end up with is that the decision variables are c sub I for I from 1 to n. You're maximizing the sum of c sub I minus 1/2 double sum of y sub I times c sub I x I dot with xj times yj cj for all I and all j. So that's a way more complicated objective function. However, we note that there's now, instead of being 2n, there's just n plus 1 constraints. So that's good. There's just the sum of the yi and the ci must equal 0. and ci must be between 0 and c for all I. So that is really the trade-off between the dual and the primal. We go from minimization to maximization, and then there's a sort of switch in level of complexity between the objective function and the constraints. So now for the dual, this is a quadratic function with just much simpler linear constraints, and there are efficient algorithms to solve that form of problem. So note also now that we're ending up getting the values of the c sub I. In order to recover w and b, which is what we want to find, in the dual it turns out ci are defined so that w, the vector w, equals the sum of y sub I, c sub I times vector x sub I. So you can just easily compute w once you know the solution to this. And then you can solve for b by finding a point that's directly on the margin, and then use the equation we had from before for the equation of the line for that margin. So here's an example that we are going to solve now. This is some data that I made up with two different classes. There's x1 and x2. This is just two-dimensional data. Here is sort of a matrix of this data. And we want to know what is the equation of the linear classifier we should use. It looks off the bat like it should be something maybe going in between this group of points here. That would, of course, misclassify some points. It's kind of unclear what effect these other ones might be having, if any. So let's take a look. So this is the 2D case of the general case that we saw before. So we have decision variables w1, w2, and b. The objective function is to minimize z, which equals the square root of the sum of these. As we talked about before, you could also, to simplify things, take the square root off of this by squaring this. That would be fine. You might need to mess with the tuning parameter if you did that versus just using square root. Plus c times the sum of the c. Constraints we saw before, but we're just plugging in instead of w dot x, we now have the actual w1 times x1 sub I plus w2 x2 sub I. And the notation here, note that x1 and x2 are the two variables, and then we just add the I in that subscript to show that this is the ith observation. So you could have x1 would be x1 of the first observation, x2 3 would be x2 of the third observation, and so on. And then this is sort of using that more intuitive definition that we talked about. C we want to define so that it equals the maximum of 0 or this value. But as we'll see, we don't need to do that explicitly in order to solve. So we set this up in Excel. Here's a little screenshot, and I'm going to demonstrate how this is all going to work in Excel itself. Okay, so now we're going to look at solving the example data we just saw using Solver in Excel. So here we have just the raw data. There's 12 data points. Here's the x1, x2, and the binary y values. In practice, if you had y coded as something else, you just need to recode it as -1 and +1 for this algorithm to work. So then we convert this data into the constraints on W1, W2, and B. And so that all just comes directly from this. So for example, W1 is just x2 times I2 That's because in the definition we saw there was a y outside of a quantity times w1 x1 plus w2 x2 minus b. That was the quantity we were working with. So we want to multiply that y through to those two quantities. So this is y sub I, which in this case is y1, times w1 times x1 1 plus y1 times w2 times x2 x2 1. It's x2 first observation, and then b, because in the equation that we're using it's minus b, it's just minus this y value. So then we go through that for each of these. Luckily this is all very easy to do in Excel. Once you have the first row, you just copy down. I just put in these points as references for what each one of these is, just as sort of a reminder. So that's the data section. Here I put in a tuning parameter of 0.5. I've solved this a couple different ways, but I'm just using 0.5 here just for the sake of example, but you could put anything in there. The decision variables, we have W1, W2, B, and then 1C for each observation. So there are 12 of them. Right now they're all just set to 0 because we don't know what they're going to be. I put in just sort of first guesses for these, even though you can tell this isn't feasible. These constraints are violated. We have a negative number when it needs to be greater than 1. But just to start things off, just entered some values here so that Solver can move on from there. The minimum, this is the objective function that we want to minimize. So I actually did include the square root here just for the heck of it to be more geometrically accurate, I guess. But again, we don't really need that to be in there necessarily. So this is the square root. Let's look at what is being called here. So square root of B19 squared plus C19 squared, that's W1 squared plus W2 squared divided by 2 plus the sum of the cost terms like we were talking about before multiplied by the tuning parameter. That is just the objective function that we saw before, so that looks all good. Okay, so now moving on to the constraints. So each constraint, as a reminder, I've written here needs to be of the form y sub I and then sum of w1 x1 plus w2 x2 minus b needs to be greater than or equal to 1 minus c sub I. So that's for these first 12 constraints, one for each data point. The last 12 are much easier. These are just that c, so in this case c1 is greater than or equal to 0. Those were straightforward. So for the first of these, we have, in order to get this value, we have sum product of B2 through D2, so W1, W2, and B, or the coefficients of them rather, sum product with, we have B19 through D19 here, so that is just the coefficients of these three multiplied by W1, W2, and B in our current solution. And then that has added to it C sub 1, and that's for the reason that in our constraints we had greater than or equal to 1 minus this value I think in Excel we actually could program this in with 1 minus C on this side, but in general we always want to have all the variables on the left-hand side. So I've moved that over rather than subtracting it from there. It's added on the left-hand side. And then once again in Excel, once we have the first row, it's really easy to just go down. That's why the dollar signs are there for the values of the decision variables that we don't want to change. Although actually in this case for the C, because they're horizontal, did have to put those in manually, which was not too bad, but not as easy as copying and pasting. So that should be everything. All we need to do is see how this will look in Solver. So target cell D20, that's good. That's the one we want to minimize. Equal to minimize. Don't want to maximize that. Changing cells B19 through P19. We can see P19 is indeed the last one of those, so that's everything. Subject to the constraints, we have all greater than or equal to constraints, so we just need one thing here covering B23 through B46 greater than or equal to D23 through D46. And then let's try to solve it. So Excel's going through iterations. Hopefully moving towards an optimal solution. Okay. All constraints and optimality conditions are satisfied. That sounds good. So then we have these values of W1, W2, and B. So we will need to graph this. We'll put this into slope-intercept form and graph it. In the meantime, we'll go back to look at that. We'll also look at this being solved with a couple of different tuning parameters. One more thing to check out in Excel before we go back to the rest of the presentation. So this is, I had mentioned before, when I was first trying to solve this in Excel, I came up with sort of a more intuitive way of viewing things. I ended up finding it sort of easier to visualize based on defining C explicitly as its own value. Again, I don't know how you would implement this as an algorithm to solve in any other way than how I've set it up here in Excel, but I thought it was still pretty interesting and should give the same result as the other method, but at least within this environment, really easy to tell what's happening and see everything here. So the data, this is just the raw data, is the same as before. This is the same as before also, just getting the coefficients of W1, W2, and B the same way as we did before. We have the tuning parameter like before. Now we just have these three decision variables, and instead of having C as extra decision variables, we just define them based on the values that we already have. So this is actually just going to be, Excel has this max function. So like we talked about earlier in the presentation, the definition that we wanted for C is just maximum of 0 or 1 minus y times W1 times x1 plus W2 times x2 minus b. That's how we wanted to define C. So we can just do that in a very straightforward way here in Excel. Once again, we can just, once we have that row, we can just copy down all of these here. And originally when I had tried to solve this, I had put in constraints here, constraining, as we did in this case, to make sure that this held true. It turns out that because of the way we define C here, that was always true, because these constraints, we only needed them to get this to be true. So once I realized that, I said, hey, wait, I can just delete all of this. It was kind of surprising at first anyway. And then, so the objective function is basically the same as it was before. We have this getting the length of W basically, and then adding now the sum of Xi is up here instead of in the row, still multiplied by the tuning parameter. So we can pull this up in Solver. We're still getting the minimum of the same objective function. Now we're only changing these 3 cells, and amazingly we have no constraints here, which seems strange. So let's see what will happen when we solve this. And sure enough, it's not, I think there might be some rounding issues with so many computations happening in Excel. We're almost at precisely the same result, 0.5714, 0.5714, 2.714. That is very close. There's a very marginal difference here, which obviously is not great, but having it set up this way, I could see much easier what was happening. So for example, you can just see each value of Xi. You can see, or so when Xi equals 0, we know these are the points that are good. These are the points that are not good, that are misclassified. The ones that are greater than 1 are the ones that are totally misclassified. This one would just be in between the hyperplane and the margin. So yeah, it's pretty straightforward. I believe on this one, we can still see the locations of points based on this value also. And so I believe the reason that nobody uses this method to solve this problem to get support vector machines is because we're including this max function here, which is not a differentiable function. If you think about it, basically it's going down smoothly, and then once you hit the point 0, any negative points will just be at 0. So you end up with sort of a kink with a sharp point, and that sharp point where the slope changes immediately is not differentiable. And most algorithms, I believe, that solve minimization and maximization problems use the first and second derivative in order to find minimum and maximum points. So if you can't differentiate at a point, then that's not a viable strategy anymore. Again, I'm not certain if there exists some way of handling that. I'm not aware of one, but I still thought it's kind of cool that Excel can do this somehow. So yeah. Okay, so now we've taken these results that we got from Excel, we've graphed them in a different program. I actually just put this into R to plot the data and graph more easily because it looks better than what you can graph in Excel. So the points directly on or on the wrong side of the margin are the support vectors. As we mentioned, these are the only points that will affect the classifier. So let's see here. For example, 2, 1, which is a minus. 2, 1, minus. Again, there's some, Excel has rounding issues, but this is basically at equal to 1, meaning that it is has no slack remaining. So that's correct. 1, 2 minus likewise is at 1. Let's find some ones that are not at that point. So 4, 4 plus. That one is all good. It has slack remaining, so you could move that around and it would not affect this uh, optimization problem. So the other ones that are in that category, 1, 1, minus 1, yeah, that's true. 1.5 minus 1, also true. And then 4, 3, so that's true too. So that's all good. So this was the tuning parameter 0.5 case. Now we're going to look at what happens with some different values of C. So in this first example, we have a small value of C, 1/24. We remember talking about earlier, as C goes to 0, you are left with only the term in the objective function for maximizing the margin. And there's no concern, obviously, here paid for classifying points correctly, or very little concern anyway. Most of the red points are on the wrong side of the classifier, so that's not very useful. And I had to actually zoom out the viewing panel here to even see the lower margin because it's just blown up so big. So here's definitely a bad choice of C for this example. We would want something higher. Here's C equals 1/12. This was the default value that I saw recommended in most places, which is 1 over n, and here is 12 points. This looks much better than that, obviously. The classifier is sort of right in the middle here. This structure in this data that I chose is sort of always going to favor something going right in between these 4 points for better values of C. There will be some changes in the margin, and this classifier will change a bit, as we'll see as C goes up. Yeah, there's 4 points misclassified, which is as good as it can get, really. You can't choose one that will misclassify fewer than those. And the margins are a little bit wide, sort of at the outer range, but not absurd like they are here. Now we see increasing C even more to 1/2. It's moved the margins in a little bit narrower. Before, the margins were right here and through this point, so it's gotten 2, or actually 3 points that were within the wrong side of the margins now are right on it, which means they're not incurring any cost. The C value is equal to 0 for those points, where it was positive before. So that is an improvement. The classifier, because of, again, the way I set things up here, isn't that different. It just moved slightly over this way. So now the increasing C even more, at this point, if we were to narrow the margins even further, we can't improve the objective function because we're always going to have these 4 points misclassified somehow. These 3 points are right on the margins, so they don't incur any cost. The C value is equal to 0. So if we were to make narrower margins at all, we would just lose objective function value from having a narrower margin, and we would never get any better classification of points. So for any increase in C here, I tried doing this, I think, with like 8 or 10 or something, and it just ends up with the same as this. So I don't know exactly where the cutoff between 1/2 and 2 was, but just logically, you cannot get the objective function any better than that. So which of these is the best to use for our classifier? So although the margins changed dramatically with C, the hyperplane, the classifier, didn't change. That's what we were just talking about. Not very much anyway. The classification of new points is given by the sign of the value of the hyperplane if you were to plug in the new x values of a new observation. Seems in this case like an obvious choice that we would want that final solution with c equals 2, since there's the fewest possible points on the wrong sides of the margin. So why would we ever want to go with a lower c with more training errors? The answer is, in other data, you may have to worry about overfitting, which is what we'll talk about right next. So when one point, or there's other cases where this could happen too, but here's a dramatic example. One point has a very large effect on the hyperplane. It may be better to soften things up to avoid overfitting. And this is true. You may want to use a soft margin even if you could linearly separate the data. So here's some new data that I made up. Here we actually could linearly separate this, and I'm doing this to demonstrate two things, both how you can apply the soft margin to the linearly separable case, and also why you might want to use a different value of C even if you had the not linearly separable data. So here you might want to say, well, let's pick the classifier to go right here because it perfectly divides all the data. But that could be overfitting. It could be valid that all the red points are going to be on this side and all the blue points are going to be on this side, but perhaps this is just an outlier or a fluke. So say we drew the classifier here. If a new point were to land right here, it seems much more probable that it would belong with the blue group than with the red group. So we might want to have the classifier more over here so that points in this region would be classified with blue. And so I actually put this data set into Excel also and solved this using my same Excel algorithm. This is with C equals 1/2. This is looking pretty good. The classifier went right here, the margins went here and here. We have just this one misclassified point, just one blue point on the wrong side of the margin. Nothing else. We have these a couple of support vectors. If we were to increase C really high using a C of 10 here, the cost of the misclassified points is going way, way up relative to the value of having the wider margin. And so it is in fact picking a classifier up in between these 2 points. There's no longer really any error here for misclassified points, but we're probably overfitting to this training data because any new points on this side of the line are going to be classified as red when we might want those to be blue. All right, so that is the end of what I had to talk about. Here are a couple of references that I used. The Wikipedia page actually for a support vector machine was very helpful in giving sort of a standard walkthrough. It didn't go into a lot of great detail, but it gave a very good basic framework for understanding things. I also used a very similar method to the Wikipedia method, but it was good. This UC Berkeley lecture notes, just to get a different perspective and sort of hear a similar thing explained by a different person in a slightly different way. Then also looked at the chapter on support vector machines from this textbook that we've been using in class, Introduction to Statistical Learning with Applications in R. They actually solved this problem in a very different way. They set up the constraints in a completely different way. I gave a first shot at that. Wasn't getting it to work in trying to solve it in Excel, and didn't find it quite as intuitive to figure out how everything was working as the other sources I found online, and I didn't find other sources online using this method. So I'd like to learn more about how they're doing it, but I didn't pursue it as much in terms of the algorithm for solving, but certainly all the other information that I gained from reading that chapter was definitely helpful. All right, well, I hope you enjoyed this presentation. Thanks very much.